So these are the solutions to the first tutorial set for Phys 9120. So in question 1, we're asked what is the difference between a scalar quantity and a vector quantity? Well, a scalar only has a magnitude. A vector has both a magnitude and a direction. Now in part B of this question, we're told in some cases the displacement and distance will be equal in magnitude, so the displacement being the vector and the distance being the scalar. And in other cases they will not. So we're asked to give a situation where they are equal in magnitude and then one where they're not. Okay, so the distance and displacement will be equal when the displacements are in the same direction. So for example, we could have 4 meters north and 3 meters north. In this case, the magnitude of the displacement is equal to, there's our 4 meters north and here's our 3 meters north, and they're joined head to tail, so the resultant there is 7 meters, and the distance traveled we just get by adding these two, so that's 4 plus 3, which is also 7. Now they have different magnitudes when the displacements have different directions. So when the displacement have different directions to each other, then the magnitude of the total displacement will not equal the distance. So an example of this, we could have 4 meters north and 3 meters east, in which case we have 4 there and then 3 here. So the magnitude of the displacement is given by this vector here, which we can work out with Pythagoras. So that's the square root of 4 squared, which is 16, plus 3 squared, which is 9. So that's the square root of 25, which is 5 meters. Whereas the distance here would be, like it was up here, 4 meters plus 3 meters. So the total distance traveled is 7 meters. Or another example would be 4 meters north and 3 meters south. In which case, when we add the displacements, we go north 4 meters and then south 3 meters. So the displacement is here, and that's 1 meter north, which is also not equal to the distance, which is just 4 meters plus 3 meters, or 7 meters. Okay, so in question 2, we're told that the vector A is equal to 4.5i plus 5.0j minus 1.0k. B is equal to minus 2.0i minus 3.5j plus 3.0k. And C is equal to minus 1.0i plus 2.0j minus 2.0k. And in part A, we're asked to find A plus B. So it's easiest just to add these component by component. So we will do, in the I direction, we've got 4.5 minus 2.0, That's in the I direction. Then in the j direction, we've got 5.0 minus 3.5. And then in the k direction, we've got minus 1.0 plus 3.0 k. So now we just sum these things in the brackets. So we end up with 2.5i plus 1.5j plus 2.0k. Now in part B, we're asked to find b minus c. So again, we just do this component by component. So in the I direction, we've got b, which is minus 2.0i, and then we've got minus c, so minus 1 is plus 1.0i. And then in the j direction, we've got minus 3.5 minus 2.0j. And then in the k direction, we've got 3.0 minus 2, so that's plus 2.0k. And so now we just solve what's in the brackets. So this is minus 1.0i minus 5.5j plus 5.0k. Now in part C, we're asked to find a plus b minus 2c. So again, we just do it component by component. So a in the I direction is 4.5. B in the I direction is minus 2.0, and then we've got 2c, minus 2c. So we want to do minus 2 times minus 1, which gives us plus 2. That's in the I direction. In the j direction, we've got 5 minus 3.5. Now minus 2 times 2 gives us minus 4.0. That's in the j direction. And now we're on to the k direction. So that's minus 1.0 plus 3.0, and then minus 2 times minus 2, which is plus 4.0k. And so now we solve what's in the bracket. So we've got 4.5 minus 2 plus 2, which gives us the 4.5 in the I direction. In the j direction, we've got 5 minus 3.5, which is 1.5. And then we're subtracting off 4, so that gives us minus 2.5j. So let's change this plus to a minus. So that's minus 2.5j. And then in the k direction, we've got minus 1 plus 3, so that's 2 plus 4. So that gives us 6k. So that's how we solve that problem. Okay, so in problem 3, we're asked to find for each pair of vectors the resultant vector and express the answer in both component form and in terms of magnitude and bearing. And I is east and j is north. So in part A, we're given 8.2 kilometers south and then 0.5 kilometers east. So in component form, it's quite easy. We just need to add these two together. As this is south, it's going to be in the negative j direction, and east, that will be in the positive I direction. So we can put it in component form as 0.5I minus 8.2j kilometers. Now to give it in magnitude and bearing, we're going to have to add these two vectors head to tail. So we've got our 8.2 kilometers going down, and then we've got 0.5 kilometers going to the right. And our resultant is this one down here, and we'll call this angle in here theta. Now to get the magnitude of this, we can use Pythagoras Theorem. So we're finding the square root of 8.2 squared plus 0.5 squared. When we do that on the calculator, because 0.5 is a lot smaller than 8.2 and we're squaring it, we end up with 8.2 as the magnitude. So now what we're going to need to do is find this angle. So to find this angle, we know the opposite and we know the adjacent. So using trigonometry, it's best to use tan theta. So tan theta is equal to the opposite over the adjacent. So we can write, well, tan theta is equal to 0.5 over 8.2. So then we can find the inverse tan. So theta is equal to the inverse tan of 0.5 on 8.2. When you're doing this, make sure that your calculator is in degrees mode. And this is equal to 3.489 degrees. Now there's a few different ways that we can give the bearing. One of them is to give it as a true bearing. So to give a true bearing, we measure the angle it makes clockwise from north. So we need this angle here. So let's call this phi, and hopefully you can see this is a straight line here. So theta and phi are related because they sum together to give 180 degrees, a straight line. So we can say, well, phi is going to be equal to 180 degrees minus the 3.49 degrees. And when we solve this, this is equal to 177 degrees. So one way to give this as a bearing, a magnitude and bearing, is 8.2 kilometers. And that is at 177 degrees T. Another way to do it is to give the angle as east of south. So we could also write it as 8.2 kilometers, and that's south, and then we go 3.5 degrees east. Now part B, in this one, we're told that we've got two vectors. One is equal to 0.8i minus 0.2j, and the other is equal to 0.4i plus 1.2j. Now to get the resultant component wise, it's not too bad. We just have to add them together. So we just add them component by component. So we've got 0.8 plus 0.4i plus minus 0.2 plus 1.2j. Sorry, the j should be outside the brackets there. Plus minus 0.2 plus 1.2j. And so solving this, we have 1.2i plus 1.0j. So that's the answer in component format, but now we also need to give it as a magnitude and bearing. So to do that, we can look at this resultant here and draw a little diagram to show how that looks. So we've got 1.2 here in the easterly direction, and then we've got 1.0 going up in the northerly direction. So we're going to want to get this resultant here. So to get the magnitude of this, we can do the square root of 1.2 squared plus 1.0 squared, and solving that one on the calculator, we end up with 1.6 meters. Now we're also going to need to find the angle, so we can find this angle theta in here, and again we've got the opposite and the adjacent. So we can use, well, tan theta is equal to 1.0 over 1.2, and solving that we get theta is equal to 39.8 degrees. So now if we want to give it as a true bearing, we're finding the angle here it makes with north, so we'll call that phi. So in this case, phi plus theta are going to sum to give us 90 degrees. So that is going to tell us that phi, which we need to find, is equal to 90 minus 39.8. And solving that, we get 50.2 degrees. So we can say, well, this will be 1.6 meters, 50 degrees T. Or again, we can express it here. In this case, it is going east of north. So we can say this is 1.6 meters, north 50 degrees east. Okay, and then one final one. We're given 7.5 kilometers northeast. So let's draw that. This is 7.50 kilometers. And because it's northeast, that tells us that that angle in there is 45 degrees. And then we're also given 2.25 kilometers at a bearing of 138. Okay, so a bearing is measured from north, so it's around here. So here, and these haven't been drawn to scale. This one's smaller because this one's 2.25 kilometers, and this angle in here is 138 degrees. Okay, now there are two approaches that we can use to answer this question. One way to do it is to add these two head to tail. So we can draw this one here. This is 45 degrees, which means that up there is also 45 degrees because that's 90 degrees. This is 7.50 kilometers. And then we've got this one here coming down. This is 2.25 kilometers. Now, because this is 138 degrees here, this in here is equal to 180 minus 138. So 180 minus 138 is equal to 42 degrees. So we can say, well, that in there is 42 degrees. So the resultant is going to be this one here. So one way that we can solve this is using our cosine rule. So if we label this side here A and this angle here opposite it is angle A, we can call this side B and we can call this side C, then the cosine rule tells us that A squared equals B squared plus C squared minus 2BC cos A. So we could solve this and find the magnitude for A. But I think generally this way is a little bit harder, and when we get angles which are bigger than 90 degrees, if we don't account for it properly, we can lose negative signs and things. So I think rather than using this approach, which will work if you do it correctly, it's probably easier to use the other approach, which involves breaking our two initial vectors into their components and then adding the components. So let's use that approach now. So we can break this one here into two components. So here we've got this is opposite our angle. So this is going to be 7.50 sine 45, which we can solve on the calculator, and we get 5.3033. Or if you know trigonometry well, you might recognize that that's 7.50 over root 2, which is also equal to 5.33. And this side, because it's adjacent to this angle here, this is equal to 7.50. Sorry, that's very messy writing. It's equal to 7.50 cos 45, which is also equal to 5.3033, or 7.5 on root 2. So we can write this vector here, this first one, as 5.303i. That's this one, plus 5.303j. That's that one. And now we need to also break this one here into components. So to break this one here into components, we've got a component down there and a component across here. And we worked out over here that this angle in here is 42 degrees. So this one here is opposite this angle here. So this will be 2.25 sine 42. And this one here is adjacent to it. So this one here is 2.25 cos 42. And solving this, we have got 1.5055, and here solving this, we've got 1.672. So we can write this vector here in component format as 1.506i. That's this one. Now this one's negative because it's going down in the southerly rather than the northerly direction. So 1.672j. Okay, so now if we want to work out the answers in components, we can just add our components. So we can say, well, r is equal to 5.303 plus 1.506i. And then we've got j, that's equal to 5.303 minus 1.672j. And solving that one on the calculator, we end up with 6.81i plus 3.63j. And now if we want to find the bearing, we can just work out the magnitude and the bearing from this vector here. So we've got 6.81i, so this is 6.81, and then we've got 3.63j. So to get the magnitude, we're working out this, so it's the square root of 6.81 squared plus 3.63 squared, and solving that on the calculator, we get 7.72. And then we'll want this angle in here. So we've got tan theta is equal to the opposite, which is 3.63, over the adjacent, which is 6.81, which solving gives us theta is equal to 28.059 degrees. Now to get our bearing from true north, we want this angle in here, phi, and you can see that phi plus theta is 90 degrees. So this tells us that phi is going to be equal to 90 minus 28.059. So solving that, we end up with 61.9 degrees. So we can write this as 7.72 meters, 61.9 degrees T, or 7.72 meters, and that will be north 61.9 degrees east. This is problem 4. So in this problem we've got 4 forces, and we're told that the forces must all sum to 0, and we're asked to find what the third force is. So the first force is going up like this. We've got an angle of 30 degrees with the vertical here, and it's got a magnitude of 21 newtons, and this is force 1. Now, the easiest approach to use with this problem is to break all of our forces into horizontal and vertical components. Then we can sum those components separately to work out what the third force is. So let's start by splitting force 1 into a horizontal component here and a vertical component up here. Now if that angle is 30 degrees there, because this line and this line are parallel, we must have 30 degrees up there as well. So this side here is opposite that angle there. So because it's opposite, we're going to use sine. So this will have a magnitude of 21 times sine 30. Sine 30 is equal to a half. So this is going to be equal to 10.5. And the horizontal side here, this is adjacent to the 30 degrees angle, so this is going to be equal to 21 times cos of 30, and when we solve that on the calculator we end up with 18.19. So we can say, well, F1 is equal to minus 10.5i. Now I've got the negative because this is pointing to the left, and the vertical direction is j and it's going up, so that's plus 18.19j. Now force 2 is actually a bit easier because it's just going along the x-axis in the horizontal direction, and it's got a magnitude of 15 newtons. So we can write, well, F2 is equal to 15.0i. And then what we're trying to find is F3. What's that equal to? But we're told that F1 plus F2 plus F3 are all equal to 0 when they're summed. So what we can do is just sum each of the components. So let's let F3 equal F3i in the I direction plus F3j in the j direction. And so we can say, well, 0 using this thing is equal to everything in the I direction. So we've got minus 10.5 plus 15 plus F3i, and that's in the I direction, plus in the j direction we've got 18.19. This one's got a 0, and then here we've got plus F3j in the j direction. And because this is 0, it's 0 in the I direction and it's 0 in the j direction. So this part has to equal 0 and this part also has to equal 0. So let's just start by rearranging this part here. We can rearrange this and say, well, F3i is going to be equal to 10.5 minus 15.0, and that is equal to minus 4.5. And now we can look at this part, and for this to be true, F3j must be minus 18.19. So F3j is equal to minus 18.19. So now we have our two components for our F3 vector. So let's draw them. Here we've got 4.5 pointing to the left that way, and then we've got 18.19 pointing down like that. And what we're trying to do is find this resultant here. So this is equal to 4.5 squared plus 18.19 squared. And so this is equal to 18.7 newtons. And now we also need to find this angle theta here. So this is the angle theta, which is marked on the diagram. And you can see that we've got the opposite and we've got the adjacent. So let's use tan. So tan theta is equal to 18.19, the opposite, divided by the adjacent, which is 4.5. And solving that using our inverse tan, we end up with theta is equal to 76.1 degrees. So the magnitude is the 18.7 and the direction is the 76.1 degrees. Okay, this is problem 5, and in this one we're told that the vector points at an angle 35 degrees above the horizontal, and we're told the y component is 62.1 meters, and we're asked to find its magnitude. So the best way to start this is to draw a diagram. So here's our vector. It points 35 degrees above the horizontal like that, and we know this y component is equal to 62.1 meters. We don't know the x component here, and what we're trying to find is the magnitude, which is the hypotenuse here. So let's label the hypotenuse h, and then here's our angle. We know the opposite side, 62.1. So because we want to find the hypotenuse and we know the opposite, we're going to use sine theta is equal to the opposite over the hypotenuse. The opposite side is 62.1. The hypotenuse is what we're trying to find, but we do know theta, so we can write, well, this is sine 35.0. So rearranging this, we can say, well, the hypotenuse is equal to 62.1 divided by sine 35.0. And then solving that on the calculator, we end up with 108 meters. So that's the answer to that problem. Okay, so this is problem 6. In this problem, we've got a pilot which flies in a straight line from Vectorville City to Conical City, and during the flight, she travels 872 kilometers north and 1,305 kilometers east. So let's start by drawing that on a diagram. So here we go. She's traveling north and she travels a distance of 872.0 kilometers, and east she travels 1,305 kilometers. So she doesn't fly this way and then this way. She flies in a straight line. So she's flying along this route here. Sorry, my triangle doesn't quite meet up because I'm bad at drawing. Okay, so if we label these are the two cities here. She starts at Vectorville and she ends at Conical City. Now in part A of the question, we're asked what is the distance between Vectorville and Conical City. So we just need to find the length of this side here. So this is a right angle triangle, so we can just use Pythagoras. So this is the square root of 872 squared plus 1,305 squared. Solving that on the calculator, we end up with 1,569 kilometers. So the answer to A is 1,569 kilometers. So in part B, we're asked how far north of Conical City is Trigonometric Town. So let's work out where Trigonometric Town is on our diagram here. The question goes on. She then flies from Conical City at a bearing of 12 degrees to Trigonometric Town, which is a distance of 1,009 kilometers away. So our bearing is measured from north like this. So she's going up here. This is an angle here of 12 degrees, and she flies a distance of 1,009 kilometers. So up here is Trigonometric Town. And now we're trying to work out how far north. So she's traveled this distance, and what we want to do now is break it into a northerly component, and then obviously there's going to be an easterly component as well. So we have this angle, and this is the adjacent side to this angle, and we know what the hypotenuse is. So to find the length of the northerly component here, we can use, well, this is 1009 times cos of 12, and solving that on the calculator we get 987 meters. So 987 meters, kilometers is the answer to that. Part C then says, what is the distance between Vectorville and trigonometric town? So what we want to do now is find out, well, if we drew a vector straight from there to there, what's the length of this line here? Now, the easiest way to do this is to consider the northerly component and the easterly component, and then so we'll work out what this total length is and what this total length is, and then we can just use trigonometry to get this total length here. So in the north, there's the 872 kilometers going from Vectorville to Conical City. So we've got 872 plus the 987, which we worked out in part B. So summing those, we get 1,859 kilometers. Then we need to work out the easterly component. And so we've got the 1,305 kilometers. And then we'll want to work out this length here as well. Now this is opposite the 12 degrees, so this is 1009 sine 12. So plus 1009 times sine 12, and solving this on the calculator we get 1,515 kilometers. So now what we're trying to do is work out the hypotenuse, and these two are at right angles to each other. So we can say, well, the total distance is the square root of 1,859 squared plus 1,515 squared, and solving that we get 2,398 kilometers as the total distance. Okay, so in this problem 7, we've got a boat which is crossing a river that is 1,800 meters wide. Okay, so here's our river, and the width of the river here is 1,800 meters. And the velocity of the boat relative to the water, so V of B relative to the water is equal to 4 meters per second, and that's perpendicular to the shore, so that's in this direction here, and so we'll call that the J direction, and that's meters per second. Now, just remembering what the velocity of the boat relative to the water means, that's equal to the velocity of the boat minus the velocity of the water. That's using our relative velocity equation. Now, we're also told that the velocity of the water relative to the shore is given by 2 meters per second, and we can see that's in the horizontal direction. So this is the velocity of the water relative to the shore. So the velocity of the water relative to the shore is equal to 2, and that's in the I direction. And that's meters per second, and we know that that's equal to the velocity of the water minus the velocity of the shore. Now, in part A of this question, we're asked what is the velocity of the boat relative to the shore. So we want to know what's the velocity of the boat relative to the shore, which we know is equal to the velocity of the boat minus the velocity of the shore. Now, there's a few different ways we can do this one. I think the easiest way to do it is to look at these two equations here. Let's call this one equation 1, and we'll call this one equation 2. So we're looking at this part of it here. So if we sum these two equations, 1 plus 2, then we've got on the left hand, the right hand side here, but we'll write it on the left over here. We've got the velocity of the boat minus the velocity of the water, and then we've got plus the velocity of the water minus the velocity of the shore. Okay, so that's adding these two equations on this side. Now you can see we've got minus the velocity of the water plus the velocity of the water. So those are going to cancel each other out. So that's going to be equal to the velocity of the boat minus the velocity of the shore. But this is just the velocity of the boat relative to the velocity of the shore, which is what we wanted. And when we added them, we would just, we can also just add these two. So this is equal to 4j plus 2I. So we can draw a little diagram showing how to add these. And we've got the 4 going up and then the 2 going across. And this is our resultant here. So this is the velocity of the boat relative to the shore, and we can work out its magnitude. That's 2 squared plus 4 squared, and solving that we get 4.472 meters per second. And then we also want to work out the angle. So in the diagram, this angle here is marked as theta. So this angle here is the same as this angle up here. These lines are parallel, so these are alternate angles, so they're equal. So if we're trying to work out this one, then we can say, well, tan theta is equal to opposite, which is 4 divided by 2. And solving that, we end up with theta is equal to 63.4 degrees. So the velocity of the boat relative to the shore is 4.47 meters per second at theta is equal to 63.4 degrees. Now part B asks us, how long does it take the boat to cross the river? Okay, so for how long it takes to cross, all we need to worry about is the velocity perpendicular to the shore. If it's moving downstream, that will make it land further down the stream, but it's not going to affect the time it takes for it to get across the total stream. So we can use our equation that speed is equal to distance over time. And so we know that the speed across the river is 4 meters per second. So we're only considering the perpendicular part, which is taking it across the river. The distance it has to go, that's 1,800 meters. That's this length here, the length of the river. And the time, that's what we're trying to find. So the time is equal to 1,800 divided by 4. And solving that, we get 450 seconds, which we can leave it that way, or if we want, we can divide by 60, and that gives us this is equal to 7.5 minutes. So this is problem 8. In this problem, we're told that relative to the ground, a car has a velocity of 16 meters per second directed due north. So here it is going north, it's 16 meters per second, and this is the velocity of the car relative to the ground, and it is 16.0. We'll call this the J direction, and that's meters per second. And just remember that the velocity of the car relative to the ground is the velocity of the car minus the velocity of the ground. Now, we're also told that relative to this car, a truck has a velocity of 24 meters per second directed 52 degrees east of north. So let's draw a little diagram over here. This is going this way. It is 24 meters per second, and it is 52 degrees east of north. And this is the velocity of the truck relative to the car, which is the velocity of the truck minus the velocity of the car. And we're asked, what is the truck's velocity relative to the ground? So what we want is the velocity of the truck relative to the velocity of the ground, which we can write as the velocity of the truck minus the velocity of the ground. Now, in order to get this, you'll note that if we add this to this, then we've got plus the velocity of the car here and minus the velocity of the car there. Now, these are all vectors. So we can say, well, this is the velocity of the truck minus the velocity of the car plus the velocity of the car minus the velocity of the ground. And this thing here is the velocity of the truck relative to the car, and this thing here is the velocity of the car relative to the ground. So this is equal to this thing here. So let's break this into components so that we've got I and j components, and then we've got this part here as components. So we'll split this into a horizontal component here and a vertical component here. Now if this angle here is 52 degrees, this angle in here must also be 52 degrees, because these are alternate angles and this line is parallel to this line. So we can say, well, here this is 24 and this is opposite, so it's times sine 52, and this one's going to be 24 times cos 52 because it's adjacent to the 52 degrees there. So we can work out what these are, and this one here is equal to 18.91, and it's in the I direction, meters per second, and this one here, solving it on the calculator, we get 14.78 J meters per second. So we can write, well, the velocity of the truck then is 18.91 I plus 14.78 J, and then we've got plus the velocity of the car relative to the ground, which is 16.0 J, and this is meters per second. And so adding the J components together, we've got 18.91 I, and then in the J direction we've got 14.78 plus 16, and when we add those we get 30.78 J meters per second. Okay, so now we've got the velocity of the truck relative to the ground as components. Let's work out what the magnitude and direction is. So we can draw here, we've got the 18.91 in the I direction, and then we've got the 30.78 going up in our J direction. So to work out the magnitude here, we use Pythagoras. So this is the square root of 18.91 squared plus 30.78 squared, and solving that we end up with 36.1 meters per second, and then we need to work out what the angle is. Let's work out this angle here. Now the useful angle that we'd like to know is the angle it makes with north, so we want that angle there, which we can see is the same as this angle here. So to work that out, we can use, well, tan theta is equal to opposite, which is 18.91, over adjacent, which is 30.78. So solving that, theta is equal to 31.6 degrees. So we can say, well, our answer is equal to 36.1 meters per second, and this is north 31.6 degrees east. That was the answer to the first part. And the next part says, how long would it take the truck to travel as far north as the car travels in 1 hour? So let's start by working out, well, how far does the car travel in 1 hour? So to get that, we can use distance is equal to the velocity times the time. So the velocity that the car is traveling relative to the ground is 16 meters per second, and the time, this is meters per second, so we need our time in seconds. So in an hour, there's 60 times 60 seconds, because there's 60 seconds in a minute, and then there's 60 minutes in an hour. So solving this, we find that the car travels 57,600 meters per second. Now we're only caring about north, so we care that the truck is traveling at 30.78 meters per second north relative to the ground. So we're now trying to work out the time it takes the truck to travel this distance. So we know that the time, rearranging this, is equal to the distance divided by the velocity. We know the distance it has to go is the same distance as the car, so 57,600 meters, and that the velocity, that's only in the northerly direction, so we're using 30.78 meters per second. And then solving this, we end up with 1,871 seconds, which if we want, we can convert into minutes by dividing by 60. So that gives us 31.1 minutes. So that's how we solve this problem. Okay, this is problem 9, the final problem. So a person looking out the window of a stationary train notices that raindrops are falling vertically down at a speed of 5 meters per second relative to the ground. Okay, so we've got rain which is falling vertically down. The speed is 5 meters per second. And so we've got that the velocity of the rain relative to the ground is equal to minus 5.00 j meters per second, using j as the vertical direction and negative as it's going down. Now, when the train moves with a constant velocity, the raindrops make an angle of 25 degrees to the vertical when moving past the window. Okay, so here's our window. Here's the vertical. And when we look at the rain now, this is an angle of 25 degrees. And we're asked, how fast is the train moving? So this here is the velocity of the rain relative to the train. So we can say the velocity of the rain relative to the train is equal to the velocity of the rain minus the velocity of the train. And we can also say, well, this is going to be the velocity of the rain relative to the ground, which we know from up here, plus the velocity of the ground relative to the train. We know that this is so because if we expand these, then this is equal to the velocity of the rain minus the velocity of the ground plus the velocity of the ground minus the velocity of the train. Those cancel out like they have in the previous questions, and then we've got the velocity of the rain relative to the velocity of the train, which is what we wanted. Okay, now we know that the velocity of the rain relative to the ground is the vertical component. That's this component down here, because the rain is falling vertically. So that there is 5 meters per second, and that is the velocity of the rain relative to the ground. And the horizontal component, which is the velocity of the ground relative to the train, this way, it comes about because of the movement of the train. The train isn't moving vertically at all. So this is the velocity of the ground relative to the train. Now, if we can work out the velocity of the ground relative to the train, then we're going to know how fast the train is going relative to the ground. These are just equal and opposite to each other. So what we want to do is find out, well, what is this one here? So looking at this triangle, we've got the angle here and we've got this side here, and we want this side. So using trigonometry, we can see that, well, tan theta is equal to the opposite, which is the velocity of the ground relative to the train, over the adjacent, which is the 5, and this is equal to tan of 25. So we can solve this and get, well, the velocity of the ground relative to the train is equal to 5 times tan 25, and solving that, we end up with 2.33 meters per second. Now, the velocity of the train relative to the ground is equal to the negative velocity of the ground relative to the train. So the speed is still 2.33 meters per second. But it tells us that if we see the raindrops falling in this direction like this, then the train itself is moving in this direction, which shouldn't really be a surprise for me because I'm sure you've experienced this phenomenon in your everyday life.